We've been talking about the three main methods of heat. That is, the three main ways that energy transfers from object A to object B. We talked about conduction, which is when they are in contact with each other and the energy is transferred directly. We talked about convection, where a fluid literally carries the energy with it as it flows. And now we're going to talk about the third method, which is radiation. Now, radiation does have a bit of a bad connotation. A lot of people, when they hear the word radiation, red flags go up, and it's something people are worried about. Honestly, that is not the right way to think of radiation because radiation is so much more. We're exposed to it all the time, and it is not harmful in the majority of circumstances. Let's talk about what radiation is. Now, radiation is just simply electromagnetic waves. That is, waves of electric and magnetic fields that propagate through space. The energy that these waves carry with them are called radiant energy. Now, it's a wave, which means you're going to have kind of this oscillation and a distance between the peaks of waves. That distance between the peaks of waves is known as wavelength. And the type of radiation we're dealing with depends completely on what that wavelength is. If it's a long wavelength, we're dealing with one type of radiation. If the wavelength is really short, it's a different type. The longest waves are AM radio waves. Slightly shorter than that is FM radio waves or TV waves, also in the same category. These are on the order of 10 to 100 meters long. That's how big one of these waves gets. Television waves, FM radio waves are about 1 meter length, so about that wide. Would be the size of one single wave. But if you get smaller, get down to microwaves. Microwaves are 10 to the minus 3. That would be roughly 1 millimeter. Okay? So you have waves that are about 1 millimeter wide. Those are known as microwaves. Yes, they're the same type of microwaves that are used in that box in your kitchen to heat up your food. Okay? That's what we use there. Infrared waves are even shorter. There's a reason why they're called infrared. I'll talk about that in a second. Sorry, this slide changed on me. Okay, back. The size of an infrared wave is roughly 1 micrometer. Okay, that's 1,000th of a millimeter. And then even shorter than that, you're talking about wavelengths of roughly 500 nanometers. 500 nanometers. And I'm sorry, trying to write this with a mouse and it doesn't work very well. There we go. 500 nanometers. That is the size of visible light. Now, all of these are different types of radiation, and we're exposed to them all the time, especially visible light. So you can see that most radiation actually is not harmful as long as it's not too intense. We get even shorter down to ultraviolet waves, which are 10 to the minus 7. That would be about 10 nanometers. And then anything smaller than that would be an X-ray. This would be this would be 100 nanometers. 10 to the minus 7th would be 100 nanometers. X-rays, this would be 1 nanometer. And then even shorter than that, we start getting into something called gamma rays. The little figure down at the bottom right of your slide, shows specifically the wavelengths of visible light. You can see that we said that visible light is around 500 nanometers. That is right here, somewhere between green and blue light, closer to green. But visible light really varies from the longest wavelengths of red light, about 750 nanometers, down to violet light, which is, about 380 nanometers, according to this graph here. So there's a wide range. Anything beyond anything longer than red, we start getting into the infrared spectrum. And anything shorter than violet, it becomes ultraviolet. All right, so that kind of shows how those fit in to the pattern. Infrared being, below, longer than red. Ultraviolet being shorter than violet. Okay, those are the different types of waves that we often deal with. Now, these electromagnetic waves do not need molecules to propagate. They just propagate through space. They could be a vacuum, it can be air, and sometimes they can even pass through solid objects as if they're a window. Okay? And we could talk more about that in a future video when we start talking about the greenhouse effect. But in a vacuum, they travel at a constant speed. It doesn't matter what type of radiation we're dealing with, they always travel at the same speed, and that is 300,000 kilometers every second. Converting that to miles, that's about 186,000 miles in 1 second. That's how fast light is. Okay? Now, one last point about radiation. We'll dive more into radiation in the next couple of videos, but as far as basics, something that's very important is that longer wavelengths of radiation actually have less energy. And the shorter the wavelength gets, the more energy that wave carries with it. That's why ultraviolet radiation can burn you. That's why X-rays can be very dangerous. Gamma rays, which are the type of radiation everyone's scared of, all those are rather dangerous, whereas AM waves and microwaves, at least to some degree, are perfectly safe and harmless. It's because of the amount of energy they carry. If you're hit by an AM radio wave, I'm not getting hit by much energy. But if I'm hit by a single X-ray, yeah, it's going to carry a lot more energy than the longer radio waves. So where does this fit into the scenario? Well, here on the surface of the Earth, we experience weather every day. This weather is generally a result of conduction and convection within the atmosphere itself and between the atmosphere and the surface of the Earth. Radiation, on the other hand, is the energy coming from the sun to the Earth, and it's what's warming us up in the first place. And it's from that heat, that extra energy we get from radiation, that makes conduction and convection possible. We're going to talk a little bit more about radiation in the next few videos, and then we'll tie everything together and see how conduction, convection, and radiation all work together to determine our weather here in our atmosphere.